So today, let's go back very quickly and look at carbon NMR. Let's see what that's about, and then finish this off, and then I can get into the next chapter, and we can start to apply all this stuff, put it all together. When you're doing these problems, the more practice you do, the better. They get to become quite straightforward. I've had people in my office this past week saying, this is fun. Okay, this is actually enjoyable. Doing these spectra is enjoyable. I'd like it to be so, because this is what scientists do. We look for data, we look for material that will help us give us answers to what's happening in our systems. And a lot of it can be done in a systematic way. You can look at these things and you can start to get better at these things quite quickly. And you see at the bottom is the approach that people take to come up with answers when you're not given a molecule. You can do a fragment. You can do fragment patterns. This can come from the NMR spectrum quite quickly if you understand the splitting patterns. A triplet tells you have two neighbors. Maybe that's a CH2 next door, stuff like that. So have a go. Ask me questions as we go along, and this can be kind of enjoyable. C13 is very useful. It is a partner to 1H. It doesn't have as much information maybe as the 1H. We don't really do integration on these types of spectra, but it is very powerful. And you put the two together, all of a sudden you've got really useful material, useful information to be able to solve problems. There's the difference in the spectra. Be very careful. Make sure that you are looking at a carbon when you should be looking at a carbon, not the other way around, or a proton. Make sure you're looking at the right spectrum. The chemical shifts are quite different. The actual x-axes are quite different based on the different nuclei. That's fairly obvious. And you will see that the general ideas of de-shielding apply, and electronegativity plays a role, and you have those numbers in front of you. So we have some fairly simple spectra in which we have what we say we've decoupled. Yes, carbon talks to hydrogen. That will be the main emphasis of the first part of today. Carbon does talk to hydrogen, they both split, and you do see patterns. But we will often use what's called a decoupled spectrum, in which we get rid of the noise. We get rid of the extra information that the hydrogen's bringing in, but you will be given that maybe in a different way. You'll be given that in a linear fashion. I'll show you that towards the end of this section. C13 spectra, fairly well laid out there, fairly nice, nice and sort of resolved. We have some nice things about, the signal is twice as big as the other. That suggests there are more of those carbons. In this case, there are twice as many of that type of carbon. And then those chemical shifts, again, on that sheet that you have in front of you, which will be on the exam again, you have access to those numbers. If you practice them, this becomes pretty straightforward. Putting the data next to each other, you can see now if you put splitting patterns from proton next to the carbon signals, you can tell an awful lot. You can tell how many different types of carbon you have. You can tell if you have any symmetry. And you can tell what we might call global symmetry, with a whole molecule you can slice it in half, or local symmetry, like a T-butyl group. All the methyl groups are T-butyl group equivalent, and we can call that local symmetry, and then you'll see simplification of the spectrum, which is quite helpful. This idea of symmetry here, I think most people are comfortable with this. If you're not, ask. The idea that you can very quickly tell between isomers. We're about to dive into alkene chemistry again, and then benzene chemistry, and there's an awful lot of reactions here that give you products that could be 1,2 disubstituted, 1,3 disubstituted, 1,4 disubstituted, and NMR spectrum, particularly carbon, can tell you which is which. They can tell you which one you've got quite quickly. So this is where we left off. This is the sort of new thing for today. You do get coupling. If you do not decouple your spectrum, which is a fairly simple experiment to do, you get shapes in the signals. And I'll just jump ahead quickly here to show you that signal, that pattern right there. That looks quite complicated. That is a carbon spectrum that looks an awful lot like a proton spectrum. And you can see shapes. I think over here on the right-hand side, I can see a quartet. Down here, I can see a triplet. Here, I can see a triplet. Here, I can see a multiplex, a whole bunch of things that aren't clearly resolved. And then down here, what shape is that? Singlet. Okay, so the singlet's fairly obvious. The singlet, from your experience, will be the carbonyl carbon on the ester. Be very careful. Ketones and aldehydes all the way down. They're a dead giveaway. All the way down around 200. Esters, amides, things like that, further upfield. And the answer's fairly simple. If you've got lone pair on this O, that lone pair is shielding that carbonyl by pushing electron density into it through resonance. If you don't have that oxygen right there, the ketone or the aldehyde is going to be much more de-shielded because you don't have that effect. But now again, the idea here, splitting patterns. This quartet tells you have a CH3 group. This triplet says a CH2, and this triplet here says a CH2. But it's not the neighboring carbons talking to each other. It's not neighboring carbons coupling, it's carbon coupling to the protons it is attached to. And that's quite different. Be careful that you make sure that you differentiate those. So there's the patterns. Here is the idea. Carbon talks to proton. If you have 3 protons attached, for the same reasons we saw with the carbon, with the H signals, the number of permutations of the alignments of the magnets, in this case you can get 4, and that gives you the 4 lines. In this case we can see here the quartet is the same shape as it would be in the proton spectrum, but this is now in the carbon spectrum. So that very quickly tells you you've got a CH3 group. You see a quartet, it tells you you've got a CH3. You see a triplet, you've got a CH2, things like that. Very useful diagnostic information to get you into a problem quite quickly. So have a look at those, make sure you're comfortable with that. If you're not sure, let me know as soon as you can, or else it gets quite tricky. Mr. Holman, are you okay? Very good. Huh? It is different, isn't it? I'm just trying to keep an eye on where everybody is. There he is. Angelo, right there. Okay, got you. There is the typical decoupled spectrum where you've taken all that information out. Now, let's be careful here. That's more complicated, but that's more useful. There is more information there. If you're given this type of spectrum, you'd often be given the couples underneath. I'm going to show you that with a couple of examples from old quiz questions in which you're given all that data in different formats. And again, why are we here? All right, it's all data-driven, right? Everybody who's in this room has got something to do with data at some point in their lives, particularly the scientists and the engineers, the physicians, the pharmacists, and all that type of people. You've got to understand how to use and read graphs. So here are a couple of questions that might show up on a quiz. But this is the type of thing that you should be ready for, and it's quite enjoyable if you're ready. At the top, you're given a formula, and you might be given the mass, and you might add up the mass very quickly and make sure that you have the right number of atoms. You're dealing with C5H10O in this example. And at the bottom, C7H5BrO. Now, you'll pick up some things very quickly, especially those in recitation. If you only have 5 carbons, can it be a benzene ring? Probably not, because benzene rings require 6 carbons, especially if you have the mass spectrum to check against. Maybe your mass suggests that it isn't C5H10O, maybe it's C10H20O2. That's something you can do very quickly just by calculating in your head what the atom should add up to and then comparing it with the mass spec, and that gives you a good starting point. So this example, it does actually correspond to C5H10O, and then you're given what I call the linear data. You're not given the graphs, you're given the linear data. I might give you both. On today's example, to get started, I give you both. The 1H NMR spectrum has at 2.47 ppm, 2H triplet. Okay, 2 H's, what do you think that might be? CH2 group, right? There's nothing tricky about this. 2.12, we have a 3H singlet. What is a 3H singlet? It's a CH3 group. Now, is it a CH3 group in an ethyl group, or is it a CH3 group not attached to anything else? No neighbors. No neighbors, right? Patterns you can get quite quickly. 1.60, we have a sextet. That tells you've got 5 neighbors. That's a CH2 group. And all the way down there, 0.94, you've got a 3-hydrogen triplet. So those little details, that T and that quartet or sextet or whatever, they tell you in the opposite direction from building up the spectrum that if I've got a sextet, I've got 5 neighbors. Yeah, I've got 5 neighbors. I've got a triplet, I've got 2 neighbors. And that's useful. Underneath that line, just to finish this up, we've got C13 data. Now, this is the linear format again, delta 207.8. Delta is the same thing as ppm. 207.8, from practice on your chart, you'll see it's a ketone or an aldehyde. You could tell from the NMR spectrum, the proton spectrum, if it was an aldehyde or not, because you'd have a proton down at 9. We don't in our spectrum, so it's not an aldehyde, it must be a ketone. After that, you could do other things. You could do the hydrogen deficiency index. You can look for the numbers of degrees of unsaturation, and that will tell you in this molecule how many. How many degrees of unsaturation in that molecule? Just the 1 by the looks of it, yeah? You have a pi bond. 1 pi bond, it's not a cycle, so just the 1. Carbonyls, maybe you've got the infrared spectrum too. All of a sudden, you've got a lot of data. Now, within the C13 spectrum, what does S stand for in this instance? What does S mean here? Singlet. And how many protons are attached if it's a singlet? None, right? So that's the carbonyl signal. And if you went over to here, T for triplet, how many protons attached? 2. And then triplet here, 2, quartet here, 3, quartet there, 3. Now you might, especially on a test sort of situation where you're a bit stressed and things are, it's very busy, you might be taking your time and spending all of this time on this problem, and you've got to be very careful now that you see what each of those little symbols mean. You can't get through these answers to the full extent that we want if you just know what the chemical shifts are. You must know what all the symbols mean, and you must know how to work in both directions, how to construct a graph and how to take a graph and come up with a structure. All right, so, the bottom is another example. How do I know this is I see a signal down at 190. How do I know this is an aldehyde and not a ketone? Well, I think down at 9.8, I have a signal for an aldehyde in the proton spectrum. And this is the last thing I'll say about this. And then, recitation office hours, we can do as much as you want. But you bounce backwards and forwards between the spectra. And you write down the clues. And you have a go at putting the thing together. And even if you don't get the whole thing, you get points because you've had a go. And most of you will be okay with this. Back into mechanism. It is gearing up towards biological systems, towards polymeric systems, things that most of you will have some interest in the future. Even the chemical engineers now are talking about taking biochem or bioorganic chemistry and things like that instead of quantum mechanics, which is probably a good idea. But you'll need to know all about functional groups. You'll need to know all about the different structures that we have to be concerned with until the end of the term. What we're going to do now is start, in a fairly simple way, talking about double bonds next to each other. Talking about pi bond next to pi bond. We're going to start off again just looking very quickly at what a pi bond is. We did a lot of chemistry last year in the addition chapter. Now we're putting 2 pi bonds next to each other. And then we'll put 3 pi bonds next to each other. And then we get 2 chapters full of benzene chemistry based on that. So alkenes are about to be very important, and they will do the same sort of things you saw before. They will do addition, and they will stabilize charges next door. Allylic cations are good, benzylic cations are good, stuff like that. Some of which we've seen, so I don't need to spend a lot of time on that. But the chemistry here now is a good review as we head into the next chapter, which is all about benzene. So I have on the slide 2 examples of what we call polyenes, polyalkenes. You have many different double bonds in those systems. And the title of the chapter, we're going to spend pretty much all of our time on that, and very little, if any, time on that. Okay? We'll talk about the conjugated systems, and I'll give you some idea about things like Diels-Alder reactions, how very useful to make 6-membered rings, and we'll pull some things out that we're not going to talk about. But we've got 2 systems here, and they look very similar in the sense that they're quite non-polar, some functionality at the end right there, but they're quite different in terms of their chemical reactivity. At the top, we have something called a non-conjugated alkene, which means that we have a break in the conjugation. A conjugated system is when you have pi bond, next to pi bond, next to pi bond, next to pi bond. In other words, a continuous, and I'll use this word again, array, a continuous array of carbon atoms that are all sp2 hybridized, and they can communicate with each other. Whereas opposed to at the top, the hybridization pattern in the middle there is sp3, and there's no p orbital, no communication. So conjugated, all the p orbitals in a row, sp2, sp2, sp2. Non-conjugated means you have some break in that connectivity. So you'll see very useful materials now. Vitamin A at the bottom has obvious medicinal properties, and arachidonic acid at the top is the molecule that goes into making all sorts of prostaglandins as sort of useful biomedical materials. So what we're going to do is define what a diene is, and then go into polyenes, and then see some chemistry. So you have different types of diene. Okay, you can see here at the top left, we have something called 1,4-pentadiene, in which the pi bonds are split. In other words, they're not next to each other. And on the top right, we have something called 1,3-pentadiene, in which the 2 pi bonds are now next to each other. And there is a difference in their stabilities, and then there will be a difference in their reactivities. We'll see that this system on the left, you know the chemistry of that molecule because it's simply 2 alkenes. The 2 alkenes act as if they were individual alkenes. Down at the bottom, this is a much more complicated system because that bond, that single bond right there, that is now going to have what we call pi character. In other words, we're going to see that the internal carbons here are sp2. They both have 1 p orbital pointing in the same direction, and if you have that requirement, you have a pi bond. So we'll see as we work our way through today that this system is localized and this system is delocalized. Now, anytime you can spread charge out, you're going to stabilize something, right? So we're spreading electron density out and going to stabilize these systems relative to each other. So isolated double bonds, regular alkene chemistry from last semester, conjugated double bonds, more of that but with a twist. Here we see the different types with some molecular orbitals from the textbook. At the top we have something called a cumulative diene, something called an allene. If you wanted to draw this out, it would look kind of odd. This molecule here, CH2, double bond C, double bond CH2. All right, that exists. It's a very interesting molecule. It's called allene. And it's kind of interesting because the middle carbon, what's the hybridization pattern? If you have 2 pi bonds, what's the hybridization pattern? sp. And if you think about the central carbon being sp and it has 2 p orbitals, what's the relationship between those 2 p orbitals? They're parallel, pointing in the same direction, 90 degrees. What are they? On an sp carbon, what direction are the 2 p orbitals pointing? Orthogonal, right? 90 degrees to each other. So what we have now is a double bond system on the left, which is straight up and down the p orbital overlapping with its neighbor, but then the next one has to be 90 degrees to it. So you've got this twisted system in which these 2 things are joined in this central carbon, and again the answer is, or the way you say this is orthogonal. So that system there has got lots of interesting properties that you could look at the graduate level. We won't do it here. That's one type of diene. Conjugated diene, again, we're working up to molecular orbital pictures again, so we can see here an attempt to show that. The idea now, a pi bond is 2 adjacent p orbitals overlapping. Well, now we have a system in which the central carbons have that same requirement. They can overlap, and the external 2 can overlap. So we'll see delocalization, which is shown on that bottom right picture. This system is conjugated and it's completely delocalized. At the bottom, isolated diene, there's a break in the conjugation. Those p orbitals on atoms 2 and 4 cannot talk to each other. The sp3 carbon gets in the way, so that's breaking up the conjugation. And that's all the definition is. Fair enough? Okay. How do we make them? Well, we can make them using the same type of chemistry we developed last year, E1 and E2. We're making a pi bond, so let's do an E1 and E2. In this example, what's happening is that the proton over here is being attacked by the base. And what's the nature of that base? What do you think about when you see that base? Large, okay? Very basic, going to go after a proton, and it's going to do that. Now, what type of reaction was that? Give me a name of that mechanism. That's an E2, right? Basic conditions, E2. And what's happened here is that the double bond now is in conjugation. So double bonds were never great. They're not as stable as pi bonds, but the overall motivation for this reaction is we've got a very powerful base that wants to become neutral. We can dump the negative charge onto the bromine by doing this E2 reaction, and that results in a pi bond. But now it's a better system because it is conjugated. And we'll see conjugation as a motivation for finishing off reactions a little bit later. Down at the bottom, we've got a possibility now where we could take off a proton at one end, and then we can take off a proton at the other end. So you might need to see this excess in that situation, and that can give you a diene also. So those E2 reactions are very reliable, and I think fairly simple in terms of stuff we've already seen. Well, in terms of evidence, we're saying now that this central bond has some interesting characteristics. That central bond, the way it's drawn, looks like a sigma bond, right? It looks like a single bond. But it isn't simply a single bond. The pi electrons are spread across it. And you're spreading 4 electrons over the whole system. And so what we're going to say is that this atom will have hindered rotation. The rotation around that bond will be slowed down because it's partly a pi bond. If we see now evidence, okay, a simple carbon-carbon single bond, for example, in ethane is 153 picometers, and it's a different by 7 in that system, so it's shorter. Pi bonds are shorter than single bonds, so there's some evidence of pi character. Write that down. I've said that a couple of times now. We've got this argument now about why that's the case. You think about the S character involved. You've got 25% in an sp3 orbital, 33% in an sp2 orbital, and so now we've got shorter bonds, stronger bonds in terms of the atoms involved. So what I'm trying to get up to so far is that that double bond system is much more complicated than anything we've seen so far. Here we go. It's exciting, isn't it? Mechanisms. All right, we need some physical evidence. For those of you who need to take PChem, even if you just take PChem 1, which everybody should, you do experiments to work out answers. You do experiments to prove energetics. You can do experiments to measure energy released when a system is reacting, if it's exothermic. And you can see here a fairly simple experiment. This is leading up to a series of experiments that you need to understand, talking about the relative reactivity of related systems. On the left of this diagram, I have a molecule that simply contains 1 pi bond. And there are 2 of them, and we're adding hydrogen to the 2 molecules, and we're measuring the energy given off. All right? So 2 isolated individual pi bonds result in the loss of 254 kilojoules per mole. You know this is exothermic because you're going from double bond to pi bond. We saw this last term. But if you measure the energy for 1 molecule and you double it, you get this number. Now, it turns out if you do that same experiment for this molecule, that number is smaller. And it's smaller by a significant amount, 15 kilojoules per mole. What that is telling you is that the diene on the right is more stable than the molecules on the left. The dienes on the right are more stable than simple alkenes. And there's the proof. So this system here is more stable than a simple alkene system. And that's what's going to lead to its different properties. Conjugation lends to stability because you can delocalize, and there's the proof. So be okay with that experiment. In both examples, you're going to butane as the answer. The product is butane, so you can measure the energy relative to each other. Because you have the same ending point, you can say that they're the same. You can measure them next to each other. So be okay with those. Now, this is just definition stuff before I really get into mechanism. We have the possibility now of what we call hindered rotation. Okay? Hindered rotation. And this single bond isn't really a single bond. Okay? It's somewhere in between a single and a pi. You've already seen that when we did delocalization. If you understand resonance, you already saw that. That results in partial bonds, where we had to draw maybe dashed lines to show the electron density. Well, that leads now to the possibility of different conformers, different conformations, different shapes in the same molecule. And I'm going to refer this S, this is the sigma, S for sigma. Around that sigma bond, the red bond that's highlighted in the molecule, you can have hindered rotation, so you can get the possibility of different conformations. Somewhat like a Newman depiction. In this case, it's going to be slowed down because of the fact that the central bond has got some pi character. So on the left, I've got S-cis, and S-cis is simply where the two pi bonds are pointing in the same direction away from that central sigma bond, the red bond. And on the right-hand side, I've got S-trans, in which those two pi bonds are pointing away in opposite directions from that central carbon-carbon bond. So it is similar to the cis and trans for alkenes, but now we're talking about something that is partly alkene and mostly single bond. Now, if you look at the bottom, with those definitions in mind, there's the S-cis, there's the S-trans. If you look at the arrow, it gives it away. It tells you that the right-hand side is actually more stable than the left-hand side. And this is an equilibrium now. This is not resonance. This is an equilibrium between different shapes, very much like Newman depictions were. This gives it away also. In the S-cis conformation for that type of system, those two hydrogens get quite close to each other. The frontier hydrogens are going to get quite close to each other and maybe even clash. And if your molecules get bigger and you start to put bigger groups on those positions, you can have a situation where it all looks like this. Now that's a bit of a problem for us because we're about to do chemical reactions in which we want this. This is our favorable desired shape of the molecule. If you don't have overwhelming steric hindrance problems, you'll have some of this in there regardless. You might have more of this, but because this is an equilibrium, that's okay. Now, equilibrium. We haven't spent a lot of time in equilibrium, we're about to. If you have, let's say, 10% of this, and you have 90% of this, how do I get my reaction to go to completion? I'm going to say that this is the only shape that reacts. That gives you the product. So how can I make all the material work? How does all the material get to react? If this is 10% looking like the one on the left that I need, and 90% doesn't look like that, what principle comes into play? Le Chatelier, right? The idea, if you take out some of that 10%, what happens to the equilibrium? It shifts to compensate. So you can eventually make this work completely. A lot of that to come up. So there's some definitions, or there are some definitions. Be comfortable with those and be able to see them. So that you can look at systems like this and decide, is this suitable for my chemistry or not? Am I going to be successful in my reaction, or is it going to fail? At the top, if you're trapped in an alkene like that, it's 100% S-cis. There's no rotation in that cycle. So that's 100% S-cis, and that's a great system for the reaction we're about to develop. This guy here, that's a superb system to be able to do what we call a Diels-Alder reaction. I'll probably get onto that on Wednesday. But we now have the two pi bonds here, two pi bonds here, for a reason that will become apparent soon. It's those two pi bonds that react. They are stuck in the S-cis conformation, and that's what we want. Down at the bottom, this molecule will not do the chemical reaction that we're about to see. It's stuck in the wrong conformation. We have to have both pi bonds pointing in the same direction so it can bond with something else. If it's stuck in the S-trans, they're pointing in exactly the wrong direction, and they can't rotate to become better than that, so this is not going to do the chemistry we want, neither is this. So from that, know what the definition means, know where it comes from, and be able to point out very quickly which one is S-cis and which one is S-trans. Right, here's some evidence. Here are some numbers for the engineers. Show me the data. Where is it? Well, there's a graph. And what it's showing you is that there is a significant barrier to rotation. When you think about a single bond, okay, the barrier to rotation is much lower than that. It's 3, 4, 5, 6 kilojoules per mole. Now it's 15. In other words, it's saying that rotation around this bond costs you quite a bit of energy. And that's because you're breaking the pi character. You're breaking the pi bond. If you're going to go and take those two p orbitals and make this thing rotate, those pi bonds have to uncouple. They have to become disconnected. And that's going to cost you energy. So at the top of this, the transition state at the top of this could be drawn as this thing over here. And the point here is that the pi orbitals on the left and the right are now 90 degrees to each other and not communicating. So you don't benefit from that extra bonding. That extra pi bonding is good. The delocalization of the electrons is good. And if you're at 90 degrees right now, you've broken that. So on the left, S-cis starts higher because of that problem over here with the interactions at the frontier carbons. And then over there on the right, we've got the diene in which it's in the trans conformation. And there is a significant barrier to get over. So think about Newman depictions. We saw all those up and down graphs last year. This is very similar to that, but it's more pronounced because you've got more bonding between those two, which you are disrupting when you rotate. Right, with that in mind, we need to start talking about MO theory again. This is very important, and it will help us explain reactivities, and it will help us explain benzene when we get there. These graphs, I might ask you to reproduce them in some form, not necessarily through memorization, but through understanding and the application of the ideas. But this goes all the way back to the very simple stuff we did with hydrogen. You think about the simple diagram we drew a long time ago to explain the molecular orbitals of hydrogen. We have the 1s orbital for H, and we have another s orbital, and we're trying to describe the H2 molecule. We've done that a number of times in the first term. It's the simplest example, that's why we do it. And you think about what this line really means in the middle, and where are the electrons, and you know, where are they populated, and how do we draw this molecule? Well, each hydrogen brings with it a 1s electron. That's its valence shell, right? And when they come to bond, they do so to benefit from becoming stable, and they become a system that is very much like an inert gas. So in this example, the bonding molecular orbital was always the one we talked about, and that was described as sigma. Now, what was this at the top? What was that described as? The antibond, right? That's sigma star. And in most, if not all, of the molecules we have seen so far, that sigma star has not been talked about. It's not been populated. But we're about to do a lot of chemistry in which we start bumping electrons up to higher levels. And this will be the basis of UV visible spectroscopy when we get there at the end of this chapter. So now this guy, the parking spot, if you like, the empty parking spot that you can go to if you need to, is going to be necessary. It's going to be needed. Well, to extrapolate very quickly, that was an H2 molecule involving one bond, and it happened to be a sigma bond. On the left-hand side of the picture here, we have the electron picture for the pi bond in an alkene. And it's the same sort of idea. Each carbon in a pi bond brings with it a p electron, and that's the atomic sort of picture right there. And then they overlap, and you can get the better bonding picture, or you can get the, I've got to be careful here, well, I'm not going to call it sigma star, I'm going to call it pi star. We now have a pi antibonding orbital that could be populated. Now, it destabilizes the system, which might happen temporarily. If you put an extra electron in there, maybe the molecule falls apart. Maybe you can induce it to do some chemistry by making it unstable, by jumping the electrons from one to the other. But the whole point of that is that we have two pictures up here. This is the picture you're used to. That's a regular pi bond in which you have two p orbitals next to each other. They're parallel, same size, same shape, they overlap, you get a pi bond. That is the pi bond. But there is an equally unstable picture in which they don't talk to each other. And we have something called a node in the middle, and you've heard the word node before, I hope, in freshman chemistry. No electron density between those two carbons. So it's the opposite examples, in which the two orbitals seem to be repelling, and therefore less stable. So we're okay, hydrogen's got two, a pi bond has two. Yep, because you're just dealing with two atoms, one next to each other. Well, you need to get to this, because in a couple of weeks, we need to get to 6 orbitals when we do benzene. So we extrapolate this further. There's not much in terms of mathematics here, it's just simple populations and simple symmetry, and hopefully understanding the concept. On the left, you know, we started out with 2 orbitals, now we've gone to 4, so we need to have 4 p orbitals. And on the left over here, we have what we call the 0 point, in which the orbitals are not talking to each other. And if you have 4 orbitals, you can't destroy orbitals, so you start with 4, you get 4, molecular. If you start with 12, you get 12, every time. We have 4 possibilities now. We have the best of all, in which bonding occurs at the bottom. We have the worst of all at the top, where no bonding occurs at all. And the next one up is some bonding. And the one above that is a little bit of bonding, but mostly no bonding. So we have 4 possibilities for those orbitals. And you see how they're all centered around the 0 point? 2 below, 2 above. Makes sense. Where the electrons will be? Well, they're going to go to the lowest energy orbitals. In this case, the bonding orbitals are full. There is no need to put any electrons in that orbital. That is empty, and the one above it is empty. That is a stable molecule. Now, if you look at the pictures, these diagrams you might struggle to draw, but you should understand them. That's completely conjugated, that's completely delocalized. Complete bonding, that's why it's so low in energy. Next one up, you get one split. That picture is almost like the double bonds are acting as individual double bonds. The two in the middle are not talking to each other. So there's one node, one breaking communication, but you still have bonding completely. A little bit higher than the one below it because you don't have delocalization, but you still have bonding. Now, as you move across to the top here, all of a sudden we've got some problems, because if you want to put electrons into this system, maybe it's a radical. Maybe it's got a radical where we've got electrons at each end, and that's unstable and highly reactive. And then at the top, no communication whatsoever. So those pi bonds are not talking to each other. There is no pi system in terms of communication. So the best will always be the one where everything's delocalized, and there might be 1 or 2 higher than that, which is still described as bonding orbitals, in which the bonding has decreased, but it's still bonding. And the whole picture is somewhere in between those pictures. Now, those are fine to draw. These can be quite quick to draw on the right. This is what you should be picking up. And we do this with little dots. You know, you take a pencil and do this quite quickly. At the bottom, this picture is now this one on the right. Without having to draw all the molecular orbitals, trying to show the delocalization, this is showing the same thing. Complete conjugation across the system, complete delocalization of that electron density. No nodes in the system. Bonding, a lot of glue holding the system together, very stable. Next one up, we have one node, and it's a pattern here. No nodes, one node, two nodes, three nodes, as we work towards benzene. In this one, this is a pi bond, that's a pi bond, but there's no communication in the middle. There's none of this extra communication that is worth energy in the middle. And that's the highest occupied molecular orbital, because that's the one that has the electrons, the highest electron density, the highest energy electrons, highest occupied molecular orbital. And the one above it, we need to know what these terms mean. The lowest unoccupied molecular orbital is the one above that, which is empty. So this one at the top is not the LUMO. It's the one above the one that has the electron density. But the pattern should make sense. We have no breaks in communication here at the bottom. It's very stable. We have one break in communication, then we have two. And can you see why this is unstable? Those orbitals are just hanging out on their own. They're not bonded to anything. That's not a good situation. And at the top, it's terrible. Nothing's talking to next door, no neighbor communication, and so no bonding at all. And so we have this increase in energy as we go from the bottom to the top, and you need to be aware of what those pictures look like so we can start talking about how to use them. So in terms of thinking about what we need to use for chemistry, because we're going to have to use some of these orbitals to stick to other things and do some addition reactions and what have you, this picture now is trying to show you that at the bottom, comparing these two bonding orbitals, the bottom is great. Everything talks to everything else, communication, great system. The top one, the problem is right there. There's a break in the communication, that's why it's higher. But, and maybe I should write it on this slide, this is completely conjugated. And this one looks like an isolated diene. Isolated alkenes. And I think in the first few slides of the chapter, we discussed the fact that the bottom is better. The conjugation is better, and we showed some numbers that describe that. So that's where that comes from. Now, what we really need to do here is use those orbitals to be able to do chemistry. And typically it's going to be the bottom two, it's going to be the bonding orbitals that will share electron density, and hopefully we'll get to somewhere more stable. So I'm going to start talking very quickly here about simple alkenes again, and thinking about the possibility of mechanism. It's given at the bottom. This is just a copy from the bottom. There's your proton, go after it. This is behaving as a base. In other reactions, we could say it's behaving as a nucleophile. A lone pair. A pi bond is a lone pair. It's shared between two atoms, but it's doing the same thing as a lone pair. So in this example, we have a powerful acid, we have a lone pair, and we can do this. That's simple acid-base chemistry. What rule is applying? I have some regioselectivity there, so what rule is applying? Markovnikov, indeed, right? Markovnikov. You could have put the proton on the tertiary carbon, that would give you a primary carbocation. That's not very good. So this all goes in this direction. All of a sudden we made a tertiary cation. What type is it? It's been a while. What type of cation is that? Tertiary, right? And so what's good about tertiary as opposed to secondary or primary? Stabilized by hyperconjugation, which is? Certainly is, right? And that's got more bonds next to it than all the other cations, so that's the best of the lot. That's part of the story. Tertiary is still better than secondary, is still better than primary. What we do now is put a pi bond in there as well. As well as the tertiary system, you put a pi bond next to that, it's even better, because you can get delocalization as well as hyperconjugation. So Markovnikov comes into play a lot in the next couple of weeks. All we did here was change the system to one that has now two pi bonds next to each other. Those two pi bonds are conjugated, they are communicating. That will make all of the difference. And the answer here will be allylic. Right? This will be allylic systems. If you understand the allylic system, which has a pi bond next to a charge, this is straightforward. It makes a lot of sense. So we have a possibility here, and I'm leading up to this. I'm going to do it once today. I'm going to come back and do it again on Wednesday because it's really tricky to put together. In this example, we are taking HBr, but we're ending up with two bromides, two different bromides. And the connections of those two different bromides depend upon whether they added at carbon 1. In this case, there's H added at 1, there's carbon 2, there's carbon 3, and there's carbon 4. We will call this the 1,2 addition product, simply because they added at carbons 1 and 2. On the other hand, In this example, H added at the end, there's 2, there's 3, and the bromine added at 4. That is the 1,4 addition product. You'll spend time on this. It turns out that the 1,2 addition product isn't as stable as the 1,4. Any ideas why? Substitution pattern, right? What is the substitution pattern on the right molecule? Di-substituted. What about the one on the left? Mono-substituted, right? So Zaitsev rule now, the idea that you want to have more groups on an alkene to help stabilize it because sp3 carbons donate to sp2 carbons, because sp2 carbons are more electronegative, all going back to last semester. So it turns out the one on the right is more stable. And my argument coming up is that the one on the left is formed faster. I think that says faster in some language. Thermodynamic, kinetic. I haven't really used those terms yet. About to use them a lot. Thermodynamic one, the right is favored at higher temperatures. Kinetic one on the left is favored at lower temperatures. We have to get our heads around why that's the case, and so how we can control this reaction to make it go where we want it to. Mechanistically, this is the first real new mechanism that you haven't seen yet. It's very similar. It's just adding on to pieces you saw last year. There's your double bond. In this example, it does not matter which double bond I use because they're both the same. And again, this molecule is more complicated than it looks. This picture that we've drawn with 2 alkenes there is not telling you the whole story. That central single bond has got some pi character, and it's not freely rotating as well as it could be. But we can still use it because this now is a base, this is an acid, and we can do exactly what we did last time or last slide with the Markovnikov addition. That gets you to there. And all of a sudden, we have the possibility of delocalization. Okay? We are spreading this charge out. It only happens if the charge is next to the pi bond. If you put the charge here, you can't get delocalization. The pi bond is too far away. So if you don't like resonance, you don't remember resonance, go back and have a look again for some of the requirements. If we put the charge here on this secondary carbon, it is no longer simply secondary. It is now allylic. Put it next to a pi bond, it's more stabilized by resonance. And away we go. We can see delocalization here. And so really what that charge thing looks like, if I were to draw this out in a sort of a better way, we might put some dashed line here, and some dashed line there, and then some dashed line there. Maybe draw the resonance hybrid. And then where does the charge go? Well, I think I've got some charge here, delta plus at the end, and I got some charge here, delta plus. I've got 2 different positive places, 2 different electrophilic centers. Maybe write that down. The allylic cation can be attacked at 2 different places because it has 2 electron deficient carbons. 2 electrophilic centers. So now what we're going to do is think about how this works. We're going to put together maybe some diagrams, some graphs. We're going to draw the mechanism again. We're going to worry about the outcomes here. And the very first thing I'll say before I talk about that slide for 5 minutes is this. You have a choice in that first step. You could put the proton here or you could put the proton there. All you get is this. All you get is that, where the proton went on the end and you put the charge in the middle. Why not this? What's the problem with that? That's the other possibility of the anti-Markovnikov addition of that proton. Why isn't that formed? It's primary and it's not allylic. Yeah, it's awful. So now you have this big difference like we had last year with primary and tertiary cations, except this cation is better than a tertiary. So the difference is huge on the reaction profile, and all the molecules will go the easy pathway. They'll all go through the allylic system and not through that primary system. So you get exclusive formation of those 2 products. But what I'm trying to do here is set up this slide. I'm just coming up with definitions. You've got a couple of days to read through it, and then we can start to think about the outcomes. To get this finished today, this is where the 2 products come from. You have a carbocation which has the characteristics of this, which looks like secondary allylic, and this, which looks like primary allylic. I want to say this carefully now, and I'll say it again on Wednesday, and I'll say it again in recitation. We do not have 2 carbocations here. We do not have this carbocation on the left and this carbocation on the right. They are the same carbocation. The reason there are 2 pictures is because the limitations we have of drawing these things. The charge is spread across the whole system. It can be attacked at the secondary carbon on the left, or it can be attacked on the primary carbon on the right. So the mechanism to finish it off is fairly simple. Once you get to the carbocation, the carbocation gets attacked. But it could be attacked here, or it could be attacked here. And when I say the carbocation, I mean one of them, the carbocation. There are not multiple, there's not a secondary and a primary. So when you're thinking about answers, when you're thinking about reading this stuff, this is not a secondary cation. This is not a primary cation. It's a cation that is somewhere in between the two of them. That's very important. After that, 1,2 addition product, 1,4 addition product. That's where they come from. Now what we'll see on this big slide that's coming up is that you can control the outcome here simply by changing the temperature. And we really haven't seen anything like that before. Control simply by changing the temperature of the mixture. To get there, we need to think about how to run this. In this example, this is adding Br2. Does the same thing with HBr. This is adding Br2. With the HBr, I had a proton there, I had a proton there. But now I'm adding bromine, Br2. And I can do that through the same sort of situation that I've just seen, in which I add, first of all, 1 Br to the end, I get a secondary light carbocation, and I trap. So that's really the same outcome, using the same language. This is 1,2, this is 1,4. There's nothing tricky there. What is tricky is this. Now, I'm going to take my time with this because it's important to get it understood.